Okay, yeah. So I'll have to introduce myself again. So it's G.R. Krishnajan Avatar, a PhD candidate at the Aerospace Engineering Department of IIC Bangalore. So this series of lectures is towards the fulfillment of my tutorials TA sessions requirement. And yeah, this is the fourth session for NPTEL course on computational quantum mechanics. So the things that for on plate today are we'll be just reviewing some of the basics of deformation gradient, various strain measures, and talking about a little bit of what we mean by polar decomposition, and then have two very important relations which will come in handy as the course proceeds. Those are the how you relate volumes between in reference configuration and that in the what you call in the spatial configuration. And another relation that we have is relating an infinitesimal area element in the reference configuration to that in the spatial configuration. And this relation is widely known as Nansen's formula. So yeah, this is the what you call goal for today. So today we'll start with just somewhat from the basics. Let me start with deformation gradient. I'll just make it quick so that we can move to solving some problems in this area. Okay, so now at first, let me ask you, or let me just, do you have any idea of the meaning of what we mean by continuum? Because continuum mechanics starts with continuum first, isn't it? So if I may ask, do you have any sort of even a faint idea about what do you mean by continuum?
So can I answer or?
Yeah, sure. Anyone, yeah. Any
Yeah,
one of us, yeah.
continuum is essentially you can define like say you have a field varying. Say you have density. Define something with density.
Okay, yeah. Hmm.
Varying through space. You should be able to define it using continuous functions. Like
Right,
in
right. Yeah,
more kind of mathematical sense. Uh,
yeah.
like so you however you zoom in so the function is still continuous. That's how there's no breakage. So that's how
Right,
I
right,
would like to define it.
right. Yeah. Actually, that's what overall it is. That the thing is, yeah, that's the exact definition. So the thing is, what we do is like, let me start. I mean, just to give an idea. So what we do is we'll start with, say, I have a body, a generic body, as I have drawn here. This is just a body, and we represent body by script B in quantum mechanics. You'll find in most of the literature. So this body B, let's consider body B. And what we do is let's try to what you call take a small element, say small cuboid or cube, say cube of edge L. Now what you do is if our L is large, say when L is large, then we find that the material are very closely what you call, it seems that material is what you call continuously distributed, as if you won't find any gaps. Now I'm just talking about a general body. I'm not talking about what you call, say, bodies with large cracks and all. I'm just considering, say, just pick up an potato itself. So usually this this schematic is often called as continuum potato in quantum mechanics literature. You'll always find this particular schematic. Now the thing is, in say you have a potato and you actually just cut out a very small cube like element from here. Now the thing is, when L is large means say of 1 centimeter. Uh, then you will find that okay, the material is continuously distributed. However, the thing is, obviously, we cannot cut it finer and finer using just some cutting instruments. So what we'll do is now we'll have to actually pierce in our own imagination, or say what we are doing is let's observe this under some microscope. I don't know how to draw a microscope, but to the best I can. something like this. Let's put a let's put this potato on small this cubic element here and observe under a microscope. Now the thing is, as you resolve further and further, say, which means that it's equivalent to that you are cutting it finer and finer. Say, say which means you are cutting it finer and finer. Say L is becoming closer and closer to say 1 mm first, and then it becomes 10 power minus 1 mm, gradually 10 power minus 2 mm, then it will become 10 power minus 6 meter, isn't it? Or which we call it one micrometer. And after that, you will find that now the material after this point, after say even 1 mm or 1 by 10 mm, the material is no longer continuously distributed. You will start finding pores in the medium, isn't it? So the thing is, there is where after say when L is of the order of 1 micrometer, or what, let me just write as 10 power minus 6 meter, then the material is no longer continuous. Is no longer continuous. So the thing is, at about 10 power minus 3 or even minus 4 meter or so, or somewhere around 10 power minus 3 meter to 10 power minus 4 to 5 meter, we don't have an exact value. Then our assumption of the material being unique continuously distribution starts breaking down. So continuous, so our assumption of material being continuous starts breaking down. So usually this is how we define quantum mechanics. I mean, in the sense that where it's applicable. So it's only applicable at the length scales of not smaller than 10 power minus 3 or 10 power 4 meter. And it also depends on the size of the problem. So say if you are solving a problem or any say finding the stress strain distribution over a body of some largest dimension to be say 1 meter or so, then 10 power minus 3 minus 4 till this level, our continuum approximation holds. After it breaks down. So it's very much also dependent on the edge length, and let me call the problem size as L. So the thing is, the element that you are choosing and the largest dimension of the problem should be very small, should be much smaller than 1. Then only this continuum hypothesis holds. Now, this is just from a physics point of view. Otherwise, after that, what happens? Then after that, you have to take into account what all microscale or all this what we call all these atomic what we call as atomistic models. You have to consider. You have to actually take molecular approach to solve our problems. Now this quantum mechanics no longer holds. So this is just from a physics point of view. Now from a maths point of view, what I'll say is, in maths point of view, we actually let's look at from two different scales. One we have is macro scale or macroscopic view, let's call it macroscopic view. This view comes from, say, we look at the problem itself. So this is the macroscopic view. And there is something known as microscopic view. Now you'll find that sometimes you'll feel that, okay, these two views are somewhat contradictory to each other. In the sense that in macroscopic view, say if we take a very small element, say this was a very small element, we actually consider it just as a point. Say this is a small element of small cubic element of edge L, then this I'll just denote as some sort it as X. X is just the identity of the cube. So X is considered to be a point. And the same X, now X here I'm just referring to as cube, isn't it? I'm just calling it as a cube. However, from a microscopic view, X is a small mass element, if you call it that way. It's a small mass element, isn't it? Now you see they look very contradictory. And what you do is you take X to be a small mass element, and any, say you define any property, say I'm denoting, say, something known as rho. Okay, so rho is some physical property. Later we'll call it as a, what do you call, later we'll call it as density, but say rho is some physical quantity. Now at microscopic view, X is a small mass element and rho is some physical quantity which is defined over it. So in this case, let's call it to be the mass of the element divided by the volume L cube. Okay, I was considering this as to be. Now this is what we call as density, isn't it? And mass M is just the mass of the element, mass of X. And then this is some sort of a, this is very much as an averaging operation, isn't it? Because we are calculating the total mass, we are weighing the mass, and then dividing by the length cube. So this gives us a single value. So this is a single value of X for property rho. Okay, now what you do is you take this property rho, and then in the macroscopic view, you where we had considered X to be a point, we actually assign rho, or assign value of rho. Now you see what happened is there are two. I mean, there is one contradiction which I'm just trying to tell you is, you know, that point is essentially, point is massless. Oh, sorry, not massless. I mean, it has no volume, isn't it? Because a point has no dimension, so no volume. However, in microscopic view, this has volume. So this is the contradiction that we are trying to actually, we have to always keep in mind. Okay, and this is what we live with in the entire field of quantum mechanics. So this is just to, as an introductory for for how we define quantum. This is some contradiction which should always be in our mind, and because of which we should always understand the applicability of that quantum mechanics is not applicable everywhere. It depends on the size of the problem, and also what are we looking at. If we are looking, say, at a problem size, as I mentioned before, of 1 meter or so length scale, then okay, then fine, we can assign material points in throughout the body and say every material point has some physical property defined over it. However, at a microscopic view, it's considered to be small small mass or volume element with for which a particular physical quantity is averaged over. So this is the thing you should always keep in mind. And now there is where, so the quantum mechanics is defined from a macroscopic view. So it's nothing but the averaging operation over throughout the domain, throughout the body, or throughout the body B. And then say if you have small element, then there will be another small element. They will all overlap with each other, but we still are trying to approximate as a sequence of points with no discontinuity. So I hope this is clear to you. If I am, I hope this is clear to you. Could you please, I mean, tell me whether these things are.
Yes, yes,
Hello.
clear,
Yes.
clear for
Okay.
me. So maybe she, I don't know.
Okay.
Yeah, she has.
Yeah. How about Ritika? Are you? I mean, was my explanation did my explanation make some sense or?
Yeah, it's okay. Like some bit of it is related to maths also, so I can
Yeah. Yes.
understand the formulation there. So because of that, I
Okay.
can
Yeah.
able to understand it.
Okay. Okay. Then it's fine. Okay. So from now we'll start our, what do you call, the actual. So from today, the quantum mechanics, or from this particular, or from week 4th, actually, the quantum mechanics actually started even in this course. Before that, it was just building some basics about tensor analysis and how do you do some tensor operations and all. So from this week 4th onwards, we have actually started the actual quantum mechanics. So today we are going to describe, first of all, different frames. So first I'll explain what is material configuration. Usually we just call it as reference configuration, and something known as deformed configuration. Okay, in reference configuration, what we do is we'll have a body at some time. At this reference simply means that we are considering a body and then applying forces over it, and then looking at how the deformation takes place and what all the internal stresses are created, what is the strains being created in that body. That comes later. So first we define what is called as reference configuration, and which we denote as B. So the body actually is B naught. Not simply implies that it's T at T is equal to 0. And the boundary of the body, which is nothing but the covering of the body, that is defined by partial B naught. I'm just following what the convention in this course right now. And then every point is assigned a value, what do you call a Poisson vector with respect to some coordinate. And since in reference configuration, you'll see that we always tend to use capital. So it's even the coordinates are denoted in capital letters. So here x1, x2, x3 are the three axes, and then every point has a coordinate. So say this point we named it as P, then this will have a Poisson vector of xp with respect to the origin. And let's take another point. Okay, and this we call it as Q, and its Poisson vector will be x vector Q, and vector I'm denoting with an underscore. Now say we have applied something to it, some force and all, then it deforms into another shape, and now the body will be designated with a symbol BT. So T here simply implies that it's at some other time, because the thing is deformation always takes with respect to time, isn't it? So here again, after what you call deformation, and let's consider this point P. So the point P, after you have applied some force, isn't it? Some force, something so as to able to deform it. So right now our study is doesn't consider forces. We are just looking at the kinematics part, that we are just understanding the motion without taking into account what all forces are or what all factors are leading to that deformation. Okay, so right now we are just looking at, even in this current module, we are just looking at kinematics aspect. In that, we'll just build up a relation for all the motion that takes place after applications of some force, and we are not considering the nature of the force. So after that, what happens is, after the application of that force, so P will be located here. Okay, and since it's in deformed configuration, we'll always denote it with a lowercase letter p. And again, with respect to this coordinate system, I will just take the coordinate system, and if I'll just to make myself clear, we are considering Cartesian coordinate system, because the thing is Cartesian coordinate system. This is the one we widely use in engineering sciences, because this is the coordinate system which we live in. I mean, that's what we call as the 3D space. But in the 3D space, this is the most simplest coordinate system. This is what we call as the Cartesian coordinate system. Okay, and so we have x1, x2, x3. Mind you that it's just the same coordinate system. I have just redrawn it here. And so in this coordinate system, what happens is the original capital P gets deformed, and this we denote as x vector in small x vector P. Just to be again underscore and p, and likewise q also deforms to small q, and Poisson vector is xq. Okay, so now you'll ask, okay, but what is that function which is mapping this p, capital P to small p and capital Q to small q? So this we call as something known as a deformation mapping. It's denoted by psi. It's denoted by psi, and it takes two arguments, capital X vector, and it also evolves with time. So it also has another argument called time. Now, so it maps coordinate every point at capital X with respect to time to another point in the current configuration or the deformed configuration as X. So this psi we call as deformation mapping. So this psi is deformation mapping. Okay, now we'll use this deformation mapping to define many other what you call quantities. Now we'll just take a look at.
Excuse me,
Yeah.
the xp is here a Poisson vector, right? You said before. X,
Which one? Which?
What x refers in that?
No, it's called as
xt,
Poisson.
what x refers? Poisson.
Yeah, this is actually Poisson vector.
Like what kind of properties is having?
This
Position
this
vector. Okay.
Yeah, this Poisson vector, yes. And psi is our deformation mapping. Okay. So now let's define. So today we'll just be I'll just be reviewing the things, right? So I won't actually go into defining length, how the length deforms and all, but just okay, just for the sake, what let me define something known as a deformation gradient. So as you can see from its very name, right, it involves the words gradient. So gradient is nothing but change of something, isn't it? So in this case, gradient simply says that how does a small element of x vector, let me actually try to make use of the figure here, and I'll just write this down here. So we had talked about 2 points, capital P, capital Q, with Poisson vector x capital P vector and x capital Q vector, and then this got transformed to xp and xq. What we do is let's define as what you call a vector using both these points. So let it point from P to Q. Okay, so this defines some sort of an element, isn't it? Some line element. So say if we had a fiber and we had fiber along this direction, and we are just considering an element of that fiber, isn't it? So usually fibers are I'm sure you know that some strings and all, right? So what I'm doing is I'm just taking a small segment of this fiber and calling it point P and point Q. And then after I'm deforming it, so the fiber will still remain a fiber because here we are considering something called as continuum mechanics, in the sense that what you call material will continuously deform also at the same time, isn't it? So what deformation gradient does is it tries to give us x vector q minus xp vector. This is just a very crude way of saying, okay, I'm just using a very crude way of saying, it's not mathematically rigorous, this crude way of saying thing, that how does xq minus xp vary with respect to, so capital X q minus capital XP. So this is what deformation gradient loosely speaking is. Okay, so it's nothing but, I'll just call it this segment, let's call it dx vector, and this call it d capital X. So this is what deformation gradient is. Okay, so what it does is it relates small element, and I think this will be more clear from this relation here, that if I take something like this, that dx vector is equal to f double underscore define, it implies that it's a second order tensor. We have covered this in the previous tutorial sessions, and multiply it. Now you see, right? So what df does is it operates on a small segment in the reference configuration and transforms into something in the initial or in the current configuration. So that is the job of the deformation gradient. So deformation gradient, it only maps two small elements from the from reference to the current configuration. And we define what you call from this you can clearly see, right, that we had defined something called as a deformation mapping, isn't it? So it was x comma t. Now, so the way you define deformation gradient is f is equal to partial x vector by, and this is nothing but just, so this is what we call as deformation gradient. And deformation gradient, as you very much recall, it's a function of every point. And mind you that it's, yeah, so it's just like, yeah, so this is how we define our deformation gradient. Now using this deformation gradient, we define several strain measures. I'll just call it strain measures. So before, like I'm sure you must be familiar with the word called strain, not in the general parlance, but just in terms of physics. So what does strain imply? So a strain simply means that, say if you have some body, okay, and when you apply some load, so in this case, I'm just considering a string, applying a load at both the ends. What happens is it gets stretched, doesn't it? This is after application of the load. Now, the way we have understood strain from our higher secondary classes and all, what we were introduced at the time was that we just consider, say if this length is capital L naught, I'm just here, just capital L naught, and this length is L. So we define strain as the change in length, which is L minus L naught divided by L naught, the original length. So this is how we defined strain. I mean, a strain in terms of a 1D body. In this case, it happens to be a string. However, when we are considering a general 3D body, then we do not have as simple a def. I mean, we cannot derive the what do you call this, all these strains just by considering all these small, I mean, all these as a convoluted network of strings and all. So what we have to do is we have to actually build the terminology for strains using what we have defined just now, which is the deformation gradient. So that is the goal here, to build various definitions from strain using the deformation mapping and deformation gradient. So what we do is, let's just consider a general element. I'll just pick up this figure again because we'll be using this. I'll just take this figure here. I hope it's copying. Okay, copying. And then let's paste here. Okay. Sometimes it doesn't work. Okay. I'll just draw it again. Okay, I'll just take the important things, which is D capital X, and this P and Q, this capital X, and this something here, D small x, and this is small p. This was capital P, and this small q. Okay, what we do now is, let's define something called as a length of L. Sorry, length of dx. So you know very well that the way you can define a length of a vector is take its norm, isn't it? I mean L2 norm of a vector. So in that, what you do is take dx vector dot dx vector and take its positive square root. So this gives us the length of dx, isn't it? Likewise, length of d capital X vector is something similar, which is d capital X dot again the positive square root. Now what we do is let me just call this as ds. And mind you, this is just scalar because I'm just considering since it's square root of a scalar, right? So it's still a scalar. And in this case, I'll just call it as d capital S. So what I'm doing is let's take ds squared minus d capital X squared. So this gives us dx dot dx minus d capital X dot d capital X, isn't it? Now, when we go back to the previous slide, we found that we had for any segment of segment which is given by d capital X vector, which is this one here, it can be mapped using this deformation gradient to another small element in the current configuration, which is dx small x vector, isn't it? So what I'll do is I'll just substitute that expression here. So it is double f tensor d capital X dot f d capital X minus d capital X, I mean dot d capital X. Okay, so we'll just move to the next slide and then continue it. So I had written as d this dot minus. Okay. Now using some vector, I mean this vector and tensor properties, what we had seen is we can write this the first term here as d capital X vector dot f transpose f and dx, then minus, and we can always introduce something known as an identity matrix, right? Or an identity tensor. So identity tensor, when it operates on any vector, keeps it intact. So it will still be dx. This is just some mathematical jugglery we are doing. And I'll just, for now, I'll just call it like this. Then what we do is let's take dx common from both sides. Let's from this side we'll have transpose f, and even from right hand side such that we'll have. Okay. So this is what we are trying to define. Now this quantity, when we divide it by 2, so when we divide this quantity by 2, we have a new relation. Okay, so what we call this is, before that, let me just introduce something more. This thing here we call as C, and this is also known as right Cauchy Green deformation tensor. And what we do is we just divide the expression throughout by this quantity, which is dx squared minus d capital X squared by ds squared. And what does this give is, now you know that ds squared was d capital X dot d capital X, isn't it? So what we do is we'll just do that so that we have dx by ds dot F transpose F minus I, and likewise dx by the single and ds. And this is usually done in quantum mechanics. We just divide by 2. There is no specific reason why we are dividing this what you call expression by 2. It's just that dividing by 2 helps us to remove 2 when it comes later. We will come. I mean, we'll see such situations as we move move forward in the course. That at times the thing is, if we had not multiplied or divide this expression by 2, it would have just introduced the factor 2, and it just creates problems. So otherwise, why not we divide by 2 such that if some 2 occurs in the numerator, it will just cancel it out. So that's the only reason we divide by 2. And what I do is I'll just take this 2 even on this side and put it here. Now this quantity is very fundamental here. We call this E. Its E is a second order tensor, and it's defined as half of F transpose F minus I. Now you see that this E is also called as Green-Lagrange. Green-Lagrange strain tensor. Okay. So this is also another fundamental relation. It's also written as half of C minus I. Fine. And you see that it has certain properties. The first property is, say you had this body, okay? Just to, as an example, say you have this body. Now, say hypothetically you are applying a force F, okay? And then in a mathematical sense, you are just limiting it to 0. Fine. So what you are doing is you are applying a force, but it's equal to 0. It sounds very idiotic, but that's how it is. Okay. You are applying a force whose value is 0. So what it implies that okay, I'll just call this by some other letter, otherwise just not to make you confused. Let me denote it by capital T. T indicates here some tension. In that case, what happens is when you apply a force whose value is 0, it simply means that you're not doing anything to this body, isn't it? You are not doing anything to this string here. So when our T tends to 0. So this means that in our deformation mapping that we had, right? We had introduced something as deformation mapping. So deformation mapping, what it will do is it will say when it takes an argument X and T. So since nothing is happening to the body, it will just result in capital X, isn't it? Now, when you have X bar is equal to capital X bar, then you find that the deformation gradient is equal to partial X by partial X bar. This comes from the property of tensor to be identity, because both the numerator and denominator are the same. Now you see something. When you put F transpose, F to be I in this E, in the expression for this Green-Lagrange strain tensor, first from my intuitive point of view, if I may ask, so you have this string here, you're applying 0 tension. Will there be any strain in the system? Just asking. Could anyone of you please speak? I mean, please speak here. Hello. I hope.
Can you repeat the question, please?
Okay, so you have this string here, and you are applying a tension. However, the value of tension is 0. Will there be strain in this string?
I don't think so. If tension is 0, the strain won't come in that.
Yes, there won't be any strain, right?
Yes,
Yeah.
yes, yeah.
Now you see that you are easily able to see here. I mean that was from an intuitive point of view. Now what you see is you are actually able to see that since F the deformation gradient is identity. So when we try to find the strain, the value of strain tensor, so what it does is you put half and then I transpose I, which you know very well that I transpose still I, because the transpose of identity tensor is still identity. And if it's multiplied
Yeah,
with
right.
identity tensor, it's still an identity tensor when it's no matter to what power you raise it to, say I square, I cubed, whatever it will still remain identity tensor when it's multiplied with itself. So which means that we have I minus I is equal to 0. So this is just that was more of a thought experiment that why this expression, I mean, is valid. So you clearly see that, okay, strain is 0 when there is no deformation. Okay, now what we do is now let's proceed to something known as what do you call, we'll define like we had started with the definition here, right? That we started with ds squared minus d capital X squared is equal to d small x dot d small x minus d capital X dot d capital X. And in that, what we had done previously is we had expressed small x in terms of d capital X. Now we will do the reverse in the sense that we will still keep d small x as it is. However, we do something else this time. So from the relation dx is equal to f, what we do is let's multiply both sides by f inverse. Now you see that on the right hand side you have f inverse f dx. So you recall that f inverse, inverse of a tensor multiplied with a tensor is nothing but identity. So which means that right hand side is just dx. So which means that we have obtained the what do you call the element in reference configuration in terms of the element in the current configuration. And then we'll substitute this here. Minus f inverse. The thing is, these definitions come in handy later. So this will be this. Using a similar operation, what we'll have is dx dot again. Okay, let me simplify the expression here. Okay, let me just simplify it first. We'll call it dx, and again from the tensor properties we'll have f inverse transpose f inverse dx. And following the similar steps that we did for the previous case, we'll have dot. Now we can just call it as identity minus f inverse transpose into f inverse, and this is. And in this case, what we do is we multiply both, divide both sides by d small x squared, in the sense that we want to find the change in the element with respect to the current configuration, which is for which the length of the segment is given by d small s. And like before, we'll just multiply by half on both sides. So we'll have this, and this will again involve division with respect to s. And this as s. And I'll take half and keep it here. And this we call something known as small e. And this again is tensor. It's a second order tensor. And this is called as Almansi stress. Sorry, not stress, it's Almansi. ALMAN. I'll just write it clearly. ALMAN SI strain tensor. And what we see is it can also be described as we have another quantity called B. It's a second order tensor. It is defined as FF transpose. And what you see clearly here is that when you take B inverse, this is equivalent to saying F of F transpose inverse, and this gives us F inverse transpose into F inverse. And you see that this expression is present in the expression for in the Alman's strength tensor. Now, at first, let me tell you that B is what is called left Cauchy green tensor, or left Cauchy green deformation tensor. Now you'll ask me that, okay, why have we denoted B here in terms in lowercase letter, and while the previous what was the right Cauchy green tensor deformation tensor was in capital C. The reason being, and what let's do next is just to. So the reason being that B lies in the current configuration and capital C lies in the what do you call, in the reference configuration. Now we'll just derive why this occurs. Before that, let me just first add the expression of E in terms of half and I minus B inverse. Okay, and again E is also in small case letters because it also exists in the current configuration. Now let's just take a look at deformation gradient at first in more detail. That deformation gradient we are defined as partial derivative of small x with respect to capital X. Now in initial terms, what you see is small x lives in spatial configuration. And capital X lives in the reference configuration. Spatial or current, this I'll use interchangeably. This means the same thing, and reference configuration, you can also call it as material configuration, because it's in this configuration where we had defined all those material points. And just going by that, what we see is in spatial configuration, we also always denote things with respect to small case letters, small case letters. And in reference configurations, things or any such quantity is represented in terms of uppercase letters, or so in the other case, what lowercase, in this case, uppercase letters. Now, say as we had learned in the previous modules, that any vector can be expressed in, can be represented in any basis. So using the Einstein's notation. So E is again our Cartesian basis vectors. Okay, E is nothing special. It's just Cartesian basis vectors. So just for Ritika, so this any vector, as we had learned in our higher secondary school years, that we can represent in terms of, say, x1 e1 plus x2 e2 plus x3 e3. So what we do is when we so in each case, what we see is there are two subscripts. So x has one subscript, e has one subscript, and all it's just getting, these terms are getting added up. So effectively, when we use summation notation, it's equivalent to I is equal to 1 to 3 xi and ei vector. However, I mean, and then there is a convention called as Einstein's summation convention, in which it implies that this can be shortened further as xi. So this implies that if we have double subscript repeated in one term, it simply means that we are performing some addition operation over it. Okay, so that's what that's why I have used this very compact notation here. And in this case, you say that, okay, E is also represented in terms of I. I mean, E is in a small case letters or lowercase letters, and I is again in lowercase letters. However, if we had to represent capital X in a similar fashion, I would represent as X capital I or I'll just use not to get confused, X capital J and E. E would also be in capital, so E capital J. Now E here is different from the other E that we defined. This E is just a vector. Okay. And here it means that here again E is still the same Cartesian basis vectors, but this is just for the sake of notations that we prefer to refer everything in terms of uppercase letters when we are defining terms which belong to the reference configuration. Now, when we have f is equal to partial x with respect to capital X here, this can be written as partial of xi divided by partial of x capital J capital EJ. And this is in terms of indicial notation, it's equivalent to writing xi divided by capital Xj, and EI, this we call as the vector product with respect to EJ. So what you clearly see here is that in the indicial representation of this F, you see that one coordinate belongs to current or current configuration, and the other coordinate belongs to, or other basis belongs to the reference configuration. Now what you see is, now I'll just to move ahead further, what I'll do is say when we define a term C was defined as F transpose F. In terms of notice, what you call in terms of the indicial notations, we have to call it as say I'll just take the same expression xi divided by capital X j and E I and then capital EJ. You are taking the transpose and multiplying with, I'll just induce some says a small l or k and just l and let it be capital X M EL and then capital EM. Now after transpose, it's just that the coordinates tend to say the transpose of this tensor can be represented as then we'll just switch the order in this dyad product or the tensor product. We can write it like this as well. So this one you are multiplying with XL by capital XM, EL and EM. And then we use all that properties of vector calculus or sorry, all these tensor operations and all. So we'll have XJ and I can, these are just scalar quantities. So I'll just bring this side. Now let's operate. So EI and then EL, EM. So this leads to EI dot EL, and this is nothing but delta IL. And wherever delta IL is, so delta IL, what it will do is it will just substitute L wherever L is with I. So what we have is XI, XJ, XL by XM, and then we have EJ, tensor product with respect to, and so it was I, right? I with L with I, so I here and then EN. Now you see something here that when C is represented in terms of in some basis, what we see is C only has both this as well as this are in current, so are in reference configuration. And that's the reason we say that C belongs to, or that's why the thing is this right cosine is represented in capital letters because it belongs to reference configuration. However, for B, you will find that it's something, and then it will have E I plus, I mean this 1 EJ, signifying that since both the argument, I mean, both the operands on which this on which this tensor product is acting are in current configuration. So even B will be in current configuration. Okay, so this is that's why it's in small and this is in capital. This is just as a, because I think this was not covered in the class. So now what we'll do is let's just move ahead and I'll explain something known as polar decomposition theorem. So so Ritika, like if you are facing issues in this initial operations, I think it would be better to, I mean, just revise the week 2 of this course. So in week 2, we have all these tensor operations. So I think, and if you face any problems, then we can always discuss in the next session. And
Sure.
yeah, so yeah, the thing is that it's tough right now to explain. There are so many properties, so I think it would be good review from by revisiting or visiting those particular lectures. Okay, so what we are doing here is we are defining something known as a polar decomposition. So what polar decomposition essentially does is it takes the deformation gradient and breaks into 2 parts. So part number 1 and part number 2. Now I'm just writing in terms of some generic expression here. So either so one of 1 or 2 is a rotation matrix, rotation tensor. And likewise, if say 1 is rotation, then I'll write the other of 1 and 2 is a stretch, or what we call as it's a stretch tensor, but it's also a symmetric. It's often denoted, I'm called as a stretch here in mechanics, in quantum mechanics. So it's symmetric stretch tensor. Essentially, this tensor happens to be symmetric in nature. So there are 2 different ways. In one, what we define is F happens to be, can be defined as, or can be decomposed as, okay, that's the word we are using here, can be decomposed as R into U. Now R is nothing but the rotation tensor. And rotation tensor, as you may be knowing from linear algebra, is that it happens to be an orthogonal tensor or orthogonal matrix. And you know the property of orthogonal tensor, right? And U here is the stretch or symmetric tensor, so it's the stretch tensor. And it's also called as right stretch tensor. It's not the thing is the other is wrong. It's just here it simply implies based on the position of where the stretch tensor happens to be. So here what we see, it's on the right hand side of the rotation tensor. The other decomposition is V into R. So this is first and this is the second decomposition. Now both have their advantages, and they are used in specific context. In some context, you will use RU. It depends on how you are formulating the solution and solution strategy or solution method, or forming the governing equations or the equilibrium equations for a particular problem. So it depends on that, and we'll explore this furthermore as we proceed along the course. So right now, it's just that's what actually the idea essentially is. And V here happens to be left stretch tensor. And in both the cases, R has a property that R into R transpose is equal to R transpose R is equal to identity matrix. Fine. So this is the property of what we call as the orthogonal tensor property, right? This is the property of orthogonal tensors. So in the lecture, it has been explained much further, but due to the lack of time and we are not actually able to revise all of that. So because we also have to solve some few problems on this, so that's the reason. And however, if there are issues, we can always discuss. And let's make some connections. So we had in the previous slides discussed about C, and C was defined as F transpose F. And what we do is let's use first the right decomposition, in which case we had R and U. So we'll put R U transpose and RU transpose RU. And what will happen is sorry, it is U transpose R transpose RU. And this will, from the orthogonality property, there is nothing but I. So you know very well that U transpose, again, we had also mentioned that it's, if it's not rotation tensor, it's a symmetric stretch tensor, isn't it? So it means that U transpose will be equal to U. So there is nothing but U into U transpose, U into U. So this is, we will just denote as U square, but essentially it's just U into U from an operational perspective. And say when we are taking B here, so B is F into F transpose. So we'll have VR and VR transpose. Okay, so this will give us V R into R transpose and V transpose. So V transpose is V and R transpose is I. So this gives us V squared. Fine. Okay, so this was just trying to make connections between both. So how this C is related to U square and how B is related to V square. So that was the idea here. Okay, now let's use some ideas from linear algebra. I'll start from a new page. So from linear algebra, we know something called as spectral decomposition theorem. Spectral decomposition. In this theorem, what is done is we pick up say any symmetric tensor, okay? Say any symmetric tensor S. This you can write or express in terms of eigenvalues and eigenvectors of S. So say if S happens to be a second order tensor in three dimensions, so say it's in, so say S is an element of R 3 cross 3, then it will have three eigenvalues, isn't it? And since its S is symmetric, we know symmetric spectral decomposition for symmetric tensor. I'll just mention it explicitly here. It's only valid for symmetric tensor. So then this can be expressed in terms of summation of the eigenvalues of S, and then we have some eigenvectors, say n I, and tensor product with respect to the same eigenvector n, and this goes from I is equal to 1 to 3. So this is what we call as the spectral decomposition theorem. And we had seen from the lectures before that, okay, so if I ask that why is C symmetric, the thing is when you take C transpose, now this is F transpose F, transpose gives us F transpose into F transpose transpose. So F transpose of a transpose is nothing but the same tensor, so it's nothing but, so it's implying that A is equal to C. Likewise, even B transpose is equal to B. So since C and B are both symmetric matrices or symmetric tensors here, we can easily express in terms of the spectral representative or spectral decomposition. So we'll have C is equal to summation I is equal to 1 to 3 lambda I squared. I'm writing square for a specific reason. Okay, Now, when you look clearly at C here, so C was expressed in terms of U squared, right? As a, I mean, can be expressed as U squared. Now, say if U square, if U has, suppose, say U has eigenvalues lambda 1, lambda 2, and lambda 3. And since we know that C is equal to U squared, so can we know about the eigenvalues of C? I'm just asking. So given that the eigenvalues of U are lambda 1, lambda 2, and lambda 3, what could be the eigenvalues of C? Although the answer is clearly mentioned here. The thing is, when you have a matrix, say AX is equal to lambda X, isn't it? Now, I mean, multiply both sides by AX. So this is some eigenvalue problem. Multiply both sides by AX. So this one would be A into lambda X. See, since lambda is a scalar, you can bring it forward and let A act on X. And you know, again, from the eigenvalue problem here, that AX is nothing but lambda X. So what you see is A squared of X is nothing but lambda square of X. So it means that if you multiply the square of matrix, the eigenvalues will also be the the corresponding squares of those eigenvalues. So these are the relation. I say if you have a to the power n x, this is nothing but a to the power lambda to the power n x. So eigenvectors remain the same. It's just the eigenvalues which gets exponentiated. So in this case, likewise, you will have the eigenvalues of CR lambda 1 square, lambda 2 square, and lambda 3 square. So what we do is first we determine the eigenvalues of C. Okay. Okay. Let me explain you the process of decomposing it. So the question is, how do we find F is equal to RU, isn't it? So first what we do is let's take X. Let's take C is equal to F transpose F. We first compute this, then compute eigenvalues and eigenvectors of C. Then what we do is we take the square roots of eigenvalues, and that also positive square roots. Okay, positive square roots of eigenvalues of C. And then what you do is you can easily be defined as, so say the eigenvalues were lambda I squared, where I is equal to 1, 2, 3. And say eigenvectors are say n1, ni, and I is equal to 1, 2, 3. So what we do is now you can be expressed in terms of the square roots, right? So it's nothing but just lambda I, ni dot, tensor product with itself. So once you have U, then what you do is, and you already know the value of F. So F is known. F is known. Find C, find the eigenvalues of C, take the square roots of the eigenvalues, determine U, and then what you do is from the relation F is equal to RU, you find multiply both sides with R, or sorry, say multiply both sides with U inverse, so that this becomes I, U into U transpose identity, and identity in R acting on identity is R itself. So therefore you also have R is equal to FU inverse. So this is how you are able to obtain the value of you are actually able to decompose F in terms of rotation tensor as well as a stretch tensor. So what we'll do is next let's pick up what we call as the relations of volume changes. Okay. So how does volume change? And So I'll not go into the derivation part here. So what I'll do is I'll just try to give some explanation here. So suppose you have this cubic or even cuboidal element whose volume is dv naught, and say it undergoes some deformation phi that we had. It's just the same. Did I represent it by phi or psi? Okay, psi. Okay. So some deformation psi as a function of x comma t, and then it deforms into some element. Let's say its volume is d small v. So how is, what is the relation? So that is unknown, right? What is the relation between dv and dv naught? So what we do is, I mean, the actual expression comes to be dv is equal to j dv naught, and j here is the determinant of f. Okay, so j is also, as you call it, can be also called as Jacobian. So it's just the determinant of f. So the thing is, say if you are, when you undergo deformation, then you just determine the deformation gradient, take its determinant, multiply with the original volume element, and then you get the volume element in the deformed configuration. Okay. Now there are some terminologies here. Right? Say, what if? So how do you? When do you say that a material is incompressible? So I'm sure some of us may have come across. So when do you say that a material is incompressible?
Density stays constant.
Yeah, so actually it actually follows from the volume remaining constant. Actually, it's the otherwise. So we first say that it's the volume remains constant.
Okay.
And since you know that this is a material point, right? From a microscopic view, it's a mass element. From material point, from a microscale point of view. So the mass element, if it retains its volume even after deformation, so it means that say dv is equal to dv naught, then the way we define density, so the density is defined by element m, mass element m, or say if I'm taking it to very small, let's call it dm. So it's dm divided by, and I'll just call it capital M, just to to be consistent with our notations. However, for scalars it doesn't matter. But anyway, I'll just call it d, and it is dv naught. Now what you see is, if the same material element deforms, so that even after deformation, if you have this material m, it deforms. So the from the principle of conservation of mass, that mass can neither be created nor destroyed. It just implies that even the mass in the current configuration will still be the same, isn't it? So when it was dm in the reference configuration, even after deformation, that mass element has the same mass. However, the volume, say it's getting changed, okay, say dv. And now for incompressible flow, what happens is, and this we call as it's something, and this we can write as dm by v, nothing but j into dv naught. Okay, and this is actually a rho, and I think have I made some mistake here? Just
Yeah, I think I
please.
think I think I think
Okay,
yeah, here you have
here or not? Yes,
yeah. So J should be
yeah,
equal to 1 here.
yeah. So actually, yeah, it was here. So thanks. Yeah. Yeah, so here it should be the otherwise. Yeah, sorry. So here it should be dvj naught divided by dv divided by j from this relation, since dv naught is equal to dv by j. So that this becomes j into dm by dv. So and dm by dv is the density in current configuration rho. So we'll call it as rho naught is equal to J into rho. Now for incompressible flow, V is equal to, dV is equal to dV naught. So this implies that J is equal to 1 from this relation here, right? From this relation here, J is equal to 1. So this implies that rho naught is equal to rho. So this is how we come up with the thing that the density remains constant. We start with the first from the equivalence of volumes, then determine the value of Jacobian to be 1, and then we actually look at our density relations. And after putting J is equal to 1, we see that density remains constant. It remains the same. So yeah, that's how we define incompressibility of a material. Another thing is you very clearly see that it doesn't mean that an incompressible material cannot deform. Yes, it can, isn't it? So the thing is, incompressibility is always it's defined in terms of deformation. Okay, the thing is you cannot define what is incompressibility. Incompressibility means that you have to apply you are still subjecting it to deformation. It's just that the volume remains constant even after deformation. So that's how we define something known as incompressible here. And I'm sure that in fluid mechanics you have two things. There is a difference between incompressible fluid and incompressible flow. Yeah, we'll not talk about it here, but yeah, there is a difference between both these quantities. Both these terms, the incompressible flow and incompressible fluid. So incompressible, only for incompressible fluid do we have this relation. However, even for compressible flow, we can still have under certain consideration, we can still have the flow to be incompressible. It's just some adjustment and some particular relations being satisfied. Okay, and there is just one last thing for the review session here is what we call as the area change relations. Area change. So like we had discussed in the like very similar to volume change, we have say some let's have some area, some arbitrary area A. We call it dA, and okay, I'll just give it from an inclined view. So let this area be called dA, and there is some unit vector n. Okay, so there is unit vector to this small elemental area. Now, if it's getting deformed by that particular deformation mapping, so in some other area, this small a. So what is the relation between both these? The area in current, this is current configuration, and this is current config, and this happens to be the reference config. So the area is, this relation is given by the well-known. It's also the well-known Nansen's formula. Nansen's formula, and the way we relate both of them is n into dA is equal to J into F inverse transpose and capital N vector dA. So J is what we call as the determinant of F. So this is the famous Nansen's formula. It relates the area elements in two different configurations. Okay, so we'll just solve one problem since we are short of time. But anyway, let's just solve one problem today. Okay, I'll just pick up. Okay. So say the question is the equations of motion of a body are given in material, and mind you that I did not introduce the word, but it's also called as Lagrangian description. Material or Lagrangian description by the relation is as follows. So let's go term by, component by component. So we have x1 is equal to capital X1 plus alpha t capital X3, and likewise x2 is equal to capital X2 plus alpha t x3, and x3 is equal to capital X3 minus alpha t x1 plus x2. Okay, and alpha is a scalar, so it just is an element of R, and t is time. So our goal is to relate rho to rho naught. So we are essentially have to relate the mass densities of in both the configurations. Okay. So first of all, let me write the relation. So rho was rho naught is given by rho into j, and that's what we had learned here. That rho naught is equal to rho, j rho or rho j. So which means that we need to determine, and this can also be written as rho is equal to just rho naught by j. So we have to determine j, and j is equal to determinant of f. So which means that we need to determine f first. So f, you recall, is given by this here, and in matrix form, this is how we write it. So we'll keep along one row capital X, small x is constant, so it is x1, small x is constant, 2 and 3, and in the second row we have x capital small x2, so capital X1 and capital X2, and sorry, capital X3, and in the third row we have small x3, x1, x2, capital X3. Okay, so what we'll do is let's determine all these quantities. So let's take the first what you call array. So may I ask you to tell me what will be parcel x with respect to capital X1?
One.
Yeah, it's 1. And
The second is 0, and third is alpha t.
yes, it is alpha t. Yes, yeah. And how about the second row?
0, 1, and alpha t.
So 0, 1, and alpha t.
And
Yeah. And
minus
how about,
alpha t,
yeah,
minus alpha t, minus alpha t, 1.
yeah, minus alpha t, and 1. So I hope Ritika, you all have also understood the process. Uh,
Yeah,
yeah. Okay.
fine.
Yeah. So now what we'll do is I'll stay in the same page so that I don't have to copy everything. So determinant of f. What we'll do is let's expand along the first row here, and for the first, this is our the small submatrices that we use, right? So it's 1 into, so 1 minus into minus alpha t into alpha t, so it's 1 plus alpha t squared, and we don't need to do that for the second element because it's even if you find the principal minor, it will still get multiplied with 0, so we'll just leave it at is at 0. And for the third element in this row, we have alpha t, and then this gets multiplied by minus alpha t into 0, so 0 into minus, so plus alpha t. Okay, into alpha t. So yeah, so this gives us 1 plus alpha squared t squared plus alpha squared t squared. So this gives us 1 plus 2 alpha squared t squared. So now the relation very well, you see that we just have to substitute the expression for rho for j here, and we are able to get 1 plus. Yeah, so these are this is something which I want. This is the only problem, because the thing is this this current assignment doesn't involve a lot of, I mean, any solution. You don't have to compute anything in the solution, so I think I'll keep it at that. However, what I'll do is in the last session I had just introduced this MATLAB. So I'll still go back to MATLAB just as a refresher, because the thing is in this tutorial session we would also be continuing with dealing with some numeric solutions, because otherwise the purpose of this course is not fulfilled if it doesn't involve numerics. Okay, so the goal here is slight diversion here. So using MATLAB, I'll just start here MATLAB. I hope you're familiar with MATLAB.
Yeah.
Yeah, then it's good. At least we can then go to MATLAB. So what I'll do is I'm just picking up a very simple problem. So the problem is of fx is equal to x squared minus 3x plus 2. So we are asked to determine the roots of this of fx is equal to 0.
I have just
Yeah.
solution.
Yeah.
Do you know Python? Have you used Python anytime?
Yeah. I tend to use, yes, yeah.
Can we do? I mean, just I don't know. I mean, it's up to course. Can we do Python? I think that's much more easy and not easy. I mean, it's much more. You can take it because it's open source and it's free, right? So MATLAB we have.
Yeah.
What do you say?
Yeah. So I mean, just asking this, what you call Ritika. I mean, do you have access to Python or MATLAB? Just asking.
Actually, I'm having access to MATLAB. Can we, if you're okay with that, so you can explain in both ways, MATLAB
Okay.
and Python. Actually, I'm more comfortable with MATLAB.
Okay.
So I think Dinesh, what we should do is, I think it seems that many people that I have met, they are majorly comfortable in MATLAB.
No, I have no issues. Yeah, of course, I have no issues. I was just like,
Okay.
I think we will. So why I'm saying this is Python is free, so
Yeah,
you may
that's
not
true.
have
Yeah.
access to MATLAB. And if how many are attending the course, by the way, or we both only one, or is there anybody else joining the sessions, by the way?
I have never, I mean, so far, no. So I
No.
don't
Yeah,
think
that's
like,
what. So
yeah.
if I mean, they may not know the importance of Python, but it's okay if they're whatever the other user is comfortable with. I'm fine with it.
Yeah. So otherwise, say if someone doesn't have access to MATLAB, then there are some softwares like free mat.
Scilab
Yeah.
as well. Scilab.
Yeah,
Yeah.
even Scilab, but Scilab has slightly different commands for many things. Yeah, and it also saves the files in a different format called .si.
Okay. I
.sci actually, .sci. So either GNU Octave or FreeMat is always an open source alternative. So say if you don't always have access to MATLAB, then use FreeMat, which is just free MATLAB. It's an open source software and it has the same command structure.
That's great. Yeah.
Yeah, but anyway, the thing is, yeah, it's MATLAB
Yeah.
cannot
Go with
defeat
MATLAB.
Python. Yeah,
Go with MATLAB.
MATLAB cannot defeat Python. That's always true. Yeah. So our goal is to determine the roots of fx is equal to 0. One is using Newton-Raphson approach.
Yeah. So what Ritika is saying is she wants to move this Python MATLAB session for the next week. I think it must be intense like to. I mean, it might be too intense for us to watch. What do you say about that, Ritika? Is that what you mean?
I can't understand your question. Like, what
No,
you're asking?
no. I mean, you're saying that we will move this to the next week, right? The MATLAB thing. Were you saying that?
Yeah.
Yeah.
Okay, yeah, we can do that. That's no issue. Yes, yeah. Maybe I'll come with bunch of more good problems. This is just a
No, this
toy
is good.
problem, so
This is
yeah.
Okay.
nice. So I
So
have this
some
small question. So we will stop here, but I want to discuss small problem applied maybe like what I am looking into. Um,
sure.
can I share my screen? I think you have to access. Allow me to share the screen. Can you do
Sure.
that?
I'll just unshare it. Yeah.
I'll just show you something practical. Maybe Ritika also might be. It might be helpful for us as well. Like
Sure.
it's not my exact problem I'm trying to solve, but hopefully
Sure.
it might be useful for. I still can't present. I don't have a present option. Can you make me organizer if you don't mind?
Okay. Okay. So yeah, you are unable to access it, huh?
No, I can't. I can't
Share it.
present share the screen. Yeah.
Okay. Let me I have to make some changes to the. Okay, let me make some changes. So response options, voting options. Hello. Okay. I'm just
Maybe we should go to the participants and right click on me and maybe change it. I don't know.
okay. Is it possible? I think even this Surrey University also uses Teams, right?
Yeah, they do. I don't know if they allow me to be a presenter here. Yes.
Yeah, let me just. I think I have to
But
directly go
but
into.
I think whatever I'm sharing, it will be very much useful as in interesting to look at because whatever we have
Yeah.
discussed today,
Right.
that's what I was.
Yeah, I'm just trying to just changing some of the settings that I had initially created. Maybe okay, who can bypass the lobby? Everyone. Um, choose okay. Who can present? I'll just say everyone. Okay, I think okay, now it should work, I believe.
Okay. Just signing in from my desktop. Hello.
Yeah.
Join now. Yes, I can. Great.
Yeah.
So
Okay.
awesome. Screen one. Yeah, you can see my screen, right?
Yeah.
Yeah. So
Yes.
so so what I am doing is this is like numerical numerical investigation of rubber swelling. Okay.
Right. Yeah.
What you have is you have kind of two things. One is you have this butane inside this, like you have this rubber particle inside butane, and there's this
Hmm.
concentration difference, and something gets inside this butane rubber, and it will start to swell. You can see it swelling, right? There's this core region and
Right.
this swelling region. So this is
Yeah.
what we are trying to model.
I see.
So
Yeah.
if you look, so how would you do the volume expansion, right? This is
Huh.
so you we haven't discussed this equation 3 yet today, but we have
Right.
discussed the equation 4, the deformation gradient. You see that
Yeah.
this is what you have
Hmm.
discussed today, and
Right.
this is the Lagrangian strain tensor which was discussed
Hmm.
today, right? So what he's doing is
Yeah.
he's computing the strain. This is further divided into elastic and in inelastic form. Okay,
Right.
and
Yeah.
so the elastic is equal to this one,
Yeah.
equal to this Lagrangian stuff, but
Hmm.
the in inelastic strain is computed using this equation. Okay, and so how is it doing that? Essentially is yeah. So this is how you do the. So yeah, I just want to say that whatever equations you have used, we can actually use it. So
Yeah.
this is how you mesh it. So I don't know how to use FEM here, but however, I'm trying to do this using particle methods.
Okay.
So
Okay.
these are the equations which we actually use and research this 2019 paper. This is very
Okay.
research which is actually happening, and
I see.
very kind of hot. Yeah. So you use the diffusion equation, and you compute the inelastic strain, and you plug it into inside this F, and further compute the positions of the mesh. With because they are deforming, you will F, so you know how the mesh is deforming, right?
Right. 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 That's true. Yes.
But still, I have so the my prime aim of taking this course was I have seen this, and also I've seen this continuum mechanics equations everywhere. So like I want to know, but however I don't like there's no rule I have to like in fluid mechanics you don't have these equations.
Yeah. That's true.
Like, so I want to learn this so that I understand these equations well, and yeah. So I mean, if I understand this, it's actually done. This is like I can do like we can do like a lot of stuff using these equations. Like like literally we can model swelling of particles inside water, and several other
Right.
stuff.
Right. Right. Yeah. Yeah. Yeah.
Yeah,
Mm.
there's something to
So
we
okay.
discuss.
So which all equations? I mean, not equations. Like which all methods did they use eventually? As in.
So the point is, maybe I'll show you one more thing. Maybe you'll get an idea of what I'm talking about.
Sure. Sure. Yeah.
Uh, Lagrangian. Yeah. Okay, so not here. Let's try here. Yeah. So if you look at this, even this one, this
Right.
is published in 2019 as well.
Right.
This paper I'm looking at. So this is what you have discussed today: X, U, the row equation. I think this you will
Right.
discuss
Right.
7 and 8 in the future things,
This
and
will
then
soon come up. Yes. Soon arrive at these equations. Right. Yeah.
exactly. So you will discuss this. So the point is, so in this SPH,
Hello.
you have this
Yeah.
particle. Okay,
Yeah. Yeah.
it's not a mesh. So at each point, you'll compute F value, and you will where is this? Where is this? Yeah, you compute this F value here. You can see it, right? You can see the F value here, and the rate of change of
Yeah.
F as well, and you'll update the particle positions with time. Okay, but here it's not considering. If you look at F, it is only elastic, right? You can see it, right? It's elastic. But so elastic part is already implemented in SPH, but they haven't considered anything in elastic. Like the plastic deformation is not considered here. So for this existing formulation, which is given here, for the existing F, so now the new F, including the in inelasticity, is this one. Okay,
Right.
so
Right. Right. Right.
I take this in inelastic form and I add to the existing F thing. So I have this new F here. Right? I have this. So I'll just take it and put it inside these equations, and I can easily model the the deformation of a particle due to swelling. And when particle diffuse, when water diffuse inside a particle, it starts to swell, right? And that is modeled
Right. Right. Right.
this fixed diffusion law. J equal to it's like viscosity equation. You
Yeah.
see
Yeah.
that?
This I think is. I think I don't know whether it's fixed law. Yeah. It's fixed law. Yes. Yes. Yeah.
This fixed second law.
Right. Right. Yeah.
So you use this fixed second law. So at every each time you will compute the concentration of water inside the particle due to the diffusion. You understand what I'm saying?
Right. Right. Right.
So at every
Yeah.
time the concentration the water gets into the particle. So we compute we compute the increase in concentration due to that here. And so we know the so at any given time we know the concentration, right? So from concentration
Right. Right. Yeah.
here, yeah, you See, since you know the concentration, C, you know C, right? So you compute the this epsilon S strain free reference conflict. I don't know what this is, so you should. Epsilon S is inelastic strain caused by swelling.
Yes, yes. Okay, okay.
Epsilon S,
I
and
see.
from
Yes.
you compute the deformation. Deformation strain
I see.
inelastic. If inelastic, you put it here and you just kind of continue with your existing formulation like this, whatever.
Right, right.
You can literally model this. Literally model this swelling of this nice this thing like rubber.
Okay, I see.
So nobody has done it using SPH, like particle based methods. So there are several particle based methods, and that can be easily done.
Okay.
So if you have any questions, I can actually, I don't know. So some part I can take help from this course. So yeah, even this.
Right. I mean, what we'll try to have in the sessions. We'll also try to have some advanced numerics at the same time, because I don't think this particular course, I don't think the professor will be doing any numerics even at a later stage. So I think that should be something we should do in the tutorial session itself. Like we would be building up a big, good, such that we arrive at a very good any code even in MATLAB, but a very sophisticated one. Yes.
Correct. So if I am able to implement this thing in SPH, so I can also show that I mean this is what we discussed right throughout the course. These four equations, 1, 2, 3, 4, 5, 6, right? Only these things.
Yeah. Yes.
When I go to implement them in this SPH, I can also maybe present for 1 hour and show that this is
Sure. Yeah.
So the problems that deal with are the cracking of the object,
Yeah.
thing like that. So it's very interesting.
Right. Yeah. Okay.
Yeah. So maybe maybe if I'm able to understand that in inelastic part, then I think I want to take that back from this course. Hopefully we'll try to do that. Yeah.
Sure. Yeah.
Okay.
So I'll just stop recording. Yeah. For
Yeah.
today's
Sure.
session. Yeah. I'll stop recording.